Okay, then, so we are ready now. So sorry for the delay. Let's see. Okay, so last time we talked about flows. So that was the whole idea, just to get you confident about flows on manifolds. And now, also, because we were studying vector fields, and we saw the Lie bracket of the vector fields on a manifold. And having that bracket, we can think of it as a product. And so the space of vector fields becomes an algebra. And sometimes it is called the Lie algebra of vector fields. So now we are going to see exactly what it means to have a Lie algebra. So far, we have only defined it as a vector space, the tangent space at the identity, but there is more into it. So we will focus now for today and tomorrow for Lie groups, basically. And not only that, we will study Lie groups, but our point of view will be matrix groups, basically. So let's start now. I'm going to review the definition of a Lie group. It happens to be a group that at the same time is a manifold, and we have two important maps regarding a group, which is the product and the inverse. So once that we make the group into a manifold, we require those two maps to be smooth. And that's our definition of a Lie group. So this is a list of some Lie groups. We have seen some of them that are actually Lie groups. This is just like the sum of vectors in Euclidean space. That's a Lie group. Remember that we also cover these two because they are open sets, right? And maybe I forgot to put another one here. The set of n by n matrices. So let's put here the addition, right? That's also a group. And remember that this is Euclidean space. The sum is a polynomial function of the entries. So that's also a Lie group. But the most interesting comes up to here. Those are the ones that matter most in theory. So we prove this, and this. I'm sure we prove that those are Lie groups. For this one, we use one of the results, the constant rank theorem, I believe. But the way that we computed the manifold, we only did it for a special values of n. Today, we will see another way of computing the dimension of On. And basically, I believe that those are the ones that we have seen explicitly. There are Lie groups. Now, maybe we will see these ones tomorrow, not today. but the argument is very similar to the one that we use here. Okay. Okay, now, so we reviewed the definition of a Lie group. Okay, right, so here I'm going to recall this. That's why I'm using this. So we have the set of all non-singular matrices. And remember that we have seen that this matrix is symmetric. And here in red, you have the argument. You use properties of the transpose of matrices. So you have that. And also, when we study this, we look at the space of all symmetric matrices. Right? Now, I would like to consider a function, but first, so this is a manifold because it is an open set of Rn squared. We saw that one already, so that's a Lie group. And I would like to consider the f on the bottom has a smooth function. So there's no problem, this is a smooth, but what can you say about Sn, the set of all symmetric matrices? What type of space is it? What is the algebraic structure of the set of symmetric matrices?
It's a group.
Come again, Moises?
It's a group.
A group? Under which operation?
Multiplication of matrices.
Multiplication? Okay, let's see. So the identity is definitely a symmetric matrix. So if we are talking about the product of matrices, that will be the identity element, the identity matrix, which is there. But what can you say about the zero matrix? Is that symmetric?
Yes.
And because we are talking about the product of matrices, what is the inverse of the zero matrix?
It's not there.
Yeah, so the set of symmetric matrices is not a group under the product of matrices. So what is your next bet? I mean, basically we have two options, right? It's either the sum or the product, right? So the sum of two symmetric matrices is also a symmetric matrix, right? So this is in fact a vector space. What is the way of writing a symmetric matrix? On the diagonal, what do we have?
Anything?
It has to be symmetric, it will be anything. Okay? And what about the other entries?
The ones on the top must mirror the ones on the bottom.
So once that I put that one, this one has to be the same, right? And blah, blah, blah. So that's the general way of that you can describe a symmetric matrix. So in other words, this is basically R what? What is the dimension?
R n times n minus 1 over 2.
Right. So Sn is no other than some Euclidean space, and that's how we think about Sn as a smooth manifold. Okay? So far, the property of being a group under addition is not so important, but Sn is Euclidean space. Hence, it's a manifold, and so it makes sense. That function makes sense. It is well defined by this observation, but not only that, it is a smooth manifold, okay? And that's why we were arguing all of this, just to see why this is a manifold. Because that's Euclidean space, and so F, given like that, is a smooth manifold. Okay. And again, that map, we have seen it before, and we know that the preimage of the identity is precisely the orthogonal group. Okay? That's what we have seen. Okay, now, so again, basically, we're going to compute the dimension of this. Remember the way that we saw that it is a regular submanifold, we use the constant rank theorem, right? Of this map, it has constant rank, and we managed to prove that it's ON. And now we will argue the same to obtain the dimension, okay? So I have F. I'm going to compute the differential in something like this, and we will prove that it is onto, it is surjective, the differential. And in that way, we can compute the dimension of this. Remember, the formula is going to be the dimension of this manifold minus the dimension of this manifold. But in order to do that, we need to show that the differential is surjective. I'm taking general A, but of course, we will only require to take A on the smaller set. Right? Again, because GL is open, the tangent space can be identified with Rn squared, which is basically the set of n by n matrices. So let's compute the differential of this and then show that it is surjective, so we can compute the dimension. So let any vector, and I want to compute this at x. And for instance, this is something that we haven't seen at the first time when we saw the constant rank theorem, how to compute the differential using curves. And this is something that we have learned since then, and we will use it. So I consider any curve that makes the value a at 0 and the derivative is the vector. So then I can compute the differential of f. I want to compute this, and remember that this is the formula that we saw already. How to compute the push forward of a vector. And now we use the definition of f. Remember what f is. A goes to A transpose times A. So f applied to this matrix transpose times this one. Now, do you remember how to take the derivative here? This is something that Salvador also asked me a while ago. What is the differential for the product of matrices? It's the same product rule. So you can work it out. So I take the derivative of the first. Even the transpose goes out. Okay, the transpose is just a permutation of the entries. So you just take the derivative of the entries and then do the permutation. So this is the product rule that we have used here, right? Now let's evaluate at t equals 0. And we get this, right? So right here, there's a mistake, right? I'm computing the derivative, but I'm also evaluating. This has to be Ct of 0 because I have this. And also here, D must be 0, right? So there's a mistake there. Let me correct that and that. Right? Okay, then this is the A transpose, MX. Okay, so this is the derivative or the differential or push forward of X. We have a formula for this. And so whatever we have here, it is an element here, okay? It's a vector there. And we show that F star is surjective. So this is what we have proved. Again, I took any A, but we will be only interested in A, which is orthogonal. So this is our claim that F is surjective. And that way we will compute the dimension of ON. This is basically, so you take a vector here, and you need to come up with this vector now. Okay, notice that A is non-singular, so there's no problem doing this. Also, keep in mind this. What I want here is a vector here But the tangent space of GLN is the set of all n by n matrices. So I don't need to check nothing about X, only that it is a matrix. And for that X, if you do the calculations, you will hit V. This is what we have computed. And now replace the value of X. Here I forgot to put the transpose. Okay. And oh no, I have already done the transpose, right? Because this is X. Yes, no. The transpose of this is precisely what I wrote here in parentheses, right? You see here V transpose. And then the transpose and the inverse commute. This one, I have it here. Yeah, so that's my mistake. There's no need to put the transpose. I have already done that. Okay. Right, and now if you multiply, this cancels, so you only get dt. And that's something that I don't like. I want to have v. So is everything correct? So first of all, do you agree that I have here 1/2 vt plus 1/2 of v? That makes sense to all of you? Okay, but I don't want to prove that. I want to prove that it is equals to v. Am I doing something wrong, or why is this equals to v?
B symmetric in it.
Right. So here, the same thing that we do with the tangent space. We made that identification, right? So in particular for the symmetric matrices that previously we saw is a Euclidean space, so we usually write it like this. So yes, V is a tangent vector to the symmetric space of matrices. V is symmetric. And so we are done. Okay? Great. So now that we know that F is surjective, we can compute the dimension of ON. Remember, we have already seen a long time ago that ON was a submanifold. The result that we used, the constant rank theorem, we only showed that there was no way to compute the dimension. Later, we saw another result that will give us the dimension. And here it is. So now I will focus here. This map is surjective. And so what is the dimension? It's the dimension of the domain of F, n squared, minus the dimension of this. Moises already told us what is the dimension of Sm, because Sm is a Euclidean space, and you have it here. Okay, so that's the dimension of On. Any questions? So can you give me the values on the bottom, please? For n equals 1, what do we have?
We have
So-
1.
Sorry?
We have 1.
1, okay, what else? Sorry?
Then 3.
3?
And then 6. Then 10.
Okay, so that means that O1 has dimension 1, right? What is O1? Wait,
The line, but the origin.
sorry, Moises, come again?
The line, but the origin.
Wait, but I'm confused. I think we made some mistake because O2 has to have dimension 1, not O1. So either we have, well, I have a mistake here, or, yeah, because I mean, this doesn't match. This is wrong. Because O2 is the one that has dimension. And also, I mean, you can see that this is wrong because let's just go to the definition. Is the set of matrices 1 times 1 such that, right? So 1 by 1 matrices is just the reals. So it is the set of real numbers such that that real number times itself is 1. And this is dimension 0. Okay, so I think I made a mistake here. Let's see. Okay, so then it must be in the algebra. There's something wrong here.
I think that it should be n squared minus n plus 1 times n instead of n minus 1 times n over 2. Then you get at the end n times n minus 1 over 2.
Wait, so hold on. Okay, first of all, let's go step by step. So this is right. I mean this. Because it is an open set. Okay. So here we are right. You're saying that here we have a problem with this?
Yes.
Okay. Where is the mistake that I have here?
I think that instead of being n minus 1 times n over 2, it should read n plus 1 times n over 2.
Oh, so this is a plus?
I think so.
Yeah, I think we were missing the dimension from the diagonal.
Okay.
That's why we got n minus 1 instead of n plus 1.
Okay, so let's do this. So then here this is my mistake. Let's see. So it was the set of symmetric matrices. So this is an n by n symmetric matrix, right? In the diagonal, what do I have?
Anything?
Pardon?
Anything?
Anything? And here, like this, right? So all that I need is the upper triangular or lower triangular info. And right, so both of you are right. So this is n times n plus 1, right? Because we go all the way up to n. Yeah, so that's my mistake there. Okay, sorry about that. Now, so this becomes a plus, right? So let's see, this is 2 n squared minus n squared minus n. Okay? So we will get n and that's the mistake. Here is a n minus 1. Okay. Yeah, so now all of this makes sense now. So this is n minus 1 over 2. Okay, so again, what are the values?
0, 1,
Mhm.
3, 6.
Okay. So that's the dimension of ON for the first values of n. For n equals 1, ON is just the set of 2 points. That's dimension 0. And now what I was asking is, well, the dimension of O2 is 1. And now what can O2 be? Remember that we have discussed what are the manifolds of dimension 1.
The circle.
Right. So any connected manifold of dimension 1 is either the circle or what else?
The line.
Or the line, right? So at this point, we don't know if O2 is connected or not. It's not going to be connected. And it will happen that O2 is the disjoint union of 2 circles. Okay? In some way you have seen what O2 is. It's a square matrix such that right? And if you work out the equations, you will get a partial answer. You will get something like this. Okay, so, and if you want, like this, so determinant 1 or determinant minus 1, that will be either one circle and the other. Okay, so O2 is basically, looking at this algebraic equation, you can solve it and you can show that O2 is the union of 2 circles. Has 2 components and both of them are circles. Okay, so that's O2. And well, for the rest, I'm not going to say nothing whatsoever, just for n equals 1 and 2. Okay, great. So up to this point, any questions? Well, again, the way that I motivated this class and tomorrow's class is by describing the Lie algebra structure for a Lie group. And for that, we will need to use some concept of matrices, linear algebra, the exponential, and the calculus. So I'm going to review the matrix exponential. I'm just going to recall results. I believe that you have seen this. So just let me know as we progress. I will take any matrix, and the whole idea is to define the exponential. So we will use what we know about the Taylor series of the exponential for a number. And here it is crucial that we have a square matrix because we're going to multiply by itself. So I take the identity and then x squared, x cubed, and so on. So when I do that, if I look at each entry, so I have basically n squared series, the one that we study in calculus. For each entry, I have a power series. And it so happens that each of the entries converges. And that's how the exponential of a matrix is defined. In particular, this, so far, we can only say that it is, again, a matrix. Okay, so have you seen this before or not?
Yes.
Salvador?
I haven't.
Pardon?
I haven't.
Oh, you haven't? Okay, so the good news, Salvador, is in the book, half a page, and you will see it. The whole idea is to study each entry, and then we'll give you some bounds, and so for each entry, the series is going to converge. Sometimes this is also defined in not only linear algebra, but also in the class of differential equations. They also need this. Do you remember when you learned this, Moises? Linear algebra?
In linear algebra and for some extended topics of differential equations, yes.
Differential equations, yeah. Okay, right. Well, so Salvador, if there's something, if you go to the book and there's some, you would like to discuss something, just let me know and we will look it over.
All right. Thanks.
Right, so, well, I have it here precisely. So far, I take any matrix whatsoever, and I define another matrix. I don't know much about it, and this is precisely what we will see in a couple of minutes. We can actually say more about that new matrix. It has some very nice features, and they're very important now. Okay. So first of all, we would like to say something about the derivative of this, right? So again, I have a matrix like this. I use the scalar multiplication. I obtain another matrix, and I take the exponential of this. And I would like to compute the derivative and show that it is something like this. Well, that would be homework. Sorry for that. But at least for n equals to 1, That is true, right? It's just e to the ta, the derivative, exactly that. Okay, so for n equals 1, but you can see on the book in general. So instead, I'm going to focus on this result. So again, I have a matrix X. I define a new matrix, which I call it e to the x. And I'm going to compute the determinant of this square matrix. The formula is that this is e to the trace of x. Okay, now, I mean, this is a number, okay? This is the actual e to a number. Here is just notation for the new matrix that we define, e to the x. Now, because this is the exponential that you know very well, this is a positive function. So the determinant will always be non-zero. So we know that this is a square matrix, but we will know more. It will be a non-singular matrix. So that's part of the things that we are interested in this setting. Okay, so let's prove this. We are going to use, well, no, not here. I think not in this one. But later on, we will use this, okay? Keep it in mind. So let's prove this proposition. The determinant of an exponential of a matrix. Now, for instance, let's, before going to the proof, get used to this. What happens if X is the zero matrix? What matrix is this?
The identity?
Right, because all of this vanishes. That's the identity. And the trace of the zero matrix is 0, so we get e to the 0, which is 1. So that's perfect. Now, do you want to look at any other particular value of x, or should we move on to the proof? We move on?
Yeah, let's move on.
Well, now, I have a question before going there. So, what can you tell me about this matrix? X to be the identity. What is e to the identity? What can you say? What can you say about it? You already told me this. E to the 0 is the identity matrix. That's correct. Now, do we have a nice expression with X is the identity matrix?
We should, given that the trace is n.
No, but Salvador, so right now, forget about what I have down here. Let's just use this. So this will be the identity plus the identity, right? And then plus identity squared is identity. What can you tell me about this? Moises?
It's just the exponential matrix. I don't know how to say it.
Like this?
Yes.
And 0, right? Right, okay. Nice. Salvador, if that's okay?
Yes.
Right. Okay, so now let's move to the proof of this. We're going to prove this first for a very particular type of X. The result is for any matrix, but I'm going to take a very particular one. I'm going to take an upper triangular matrix. Okay? And let's prove this only for that type of matrices. And then we will prove it for any X. And it is a very nice proof, computations, and many aspects of linear algebra. Okay, so in the diagonal, I put A1, A2, up to AN, any numbers whatsoever. Below the diagonal 0 and above, whatever. Do you agree with this equation? X squared? I know
Yes.
what to put in the diagonal, but outside, I don't know what to put. It's more complicated, and I don't care. What can you tell me about X cubed? Correct? And so on, right? So X to the n, I know the values on the diagonal, and that's it. Below that is 0, above, I don't know. Okay? So if I look at the exponential of this, the result will be also an upper triangular matrix. Moreover, in the diagonal, I know what I have. Here, I have no idea, but in the diagonal, I have precisely the exponentials of the values of the diagonal of x. So e to the x is an upper triangular matrix, and I know what are the values on the entries of the diagonal. Okay? And what I want to prove, the equation that we would like to prove, is the determinant of this matrix. Right? So I have this. But you know that the determinant of this matrix is just the product of the elements of the diagonal. Right? But this is e to the sum, and that sum is the trace of x. And this is what we were expecting. So we are done for the proof of the theorem for a very particular type of matrix. So far, so good? Okay. Now, let's prove this in general for any x. And we will use what we have just proved, the result for upper triangular matrices. Okay. Now, here is important to look at the following, okay? Because there is something just very technical, and I want you to be aware of this. So now I'm going to take any x whatsoever. And what you know from linear algebra is that you can make x into an upper triangular matrix. Okay? However, note that here, and also these numbers, they don't have to be real, they could be complex. These are the eigenvalues of x, and they could be complex numbers, not necessarily real. Okay? But what is interesting is that we obtain a matrix of the form where the result holds. Okay? Now, let's apply E to this matrix. And right now, I'm only going to use this expression. I don't care that it looks like this. Now, before moving on, what we define above, the exponential of a matrix, I only use a matrix with real coefficients. But that definition of the exponential also works for a matrix with complex coefficients. Okay? Because this matrix has complex coefficients. Okay, so I applied the definition. But you know that this simplifies, right? What is the value of that matrix when you square that?
A x squared A inverse
Exactly. And if instead of a square we use cube or whatsoever, we get the same identity, right? So we use that to obtain this relation. Okay? And I think that's all that we need to prove the result. I want to compute the determinant of e to the x. Why this equality is true?
Because the determinant of A cancels the determinant of A inverse, since the determinant is just a number, quote unquote.
Right, so we need two results. The determinant of the product is the product of the determinants. And then, as you said, Moises, the determinant of A is the inverse of the determinant of A inverse. Right? So using that the determinant is a group morphism, basically, that's what we're using. We have this. Okay? And now I'm going to use this equation to replace this by this. There you go. Okay? Now, this is an upper triangular matrix. And we know what is the determinant of such a matrix, right? This is the trace. That's what we prove. We prove the result for an upper triangular matrix, and we use that result here. Okay? And then, what property of the traces do we use?
Is that equality correct?
Come again, Moises? What?
Is that equality correct? You wrote the determinant of e to the
Yes, right. Here I'm using what we proved at the first part. So this is upper triangular. Do you agree?
yes, but what I mean is that I think the identity we're trying to prove is that the determinant of e to the x is equal to e to the trace of x.
Oh, right. Yes. Exactly. I'm missing the E. Yeah. Right. Sorry about that. Let's see. Like this. Yes. Right. So here for this equality, we are using what we proved for the case of an upper triangular matrix, right? Because we have this. And now the trace, one property of the trace is that it is invariant under conjugation. So that's why the trace of something like this is the same as the trace of x. The trace is invariant under conjugation. Great. And in that way, we are done. Okay. Any questions on this? Right. Okay, so again, here just keep in mind that for a moment we went for the complex in order to prove this. We cannot guarantee that this is a method with real coefficients. Nice. Okay. So this result, remember that this is telling me that the determinant is always positive. It's always a positive number. In particular, it cannot be zero. So this matrix is always non-singular. So in fact, the exponential of matrices is giving me this function. I take any matrix whatsoever, and I will obtain a non-singular matrix. And again, this is more or less a generalization of this aspect. How the real line winds around the circle using complex numbers. That's the exponential that you see in complex calculus. And this is more or less what we have here. So that's why we think of M as a vector space in terms of something linear, vector space. And GL is the manifold, is the group, something that is not linear, curve, so to speak, given by this. Okay? Now, maybe in a few weeks or later, I may note the following here. Like this exponential more or less is going from a linear problem to a non-linear problem, because this is the tangent at the identity. And it is the usual drawing that we have from calculus. We have this, a point, a line, and roughly speaking, the exponential, not on the whole vector space, but on a neighborhood of the zero vector, this, something flat, it bends. You have some geometry. So from a line, the exponential will give me something curved. And that's exactly what happens here. I mean, you have the exponential 0, 1, 2, this is the identity of the group. And in a small neighborhood of 0 or any integer, you have this. So if you go from here, you are going around the circle. So from something linear in the sense of a vector space, we get something curved. Okay? So this is something from, I don't know, even fundamentals maybe. But now we have a big generalization of that concept here. Great. So we have that. So far, basically we have been doing linear algebra. So let's go back to doing a little bit of calculus or manifolds. Basically, this is the only thing that we have seen making the derivatives. But so now let's move on with manifolds and this exponential. Okay? So this map, we have seen it before, the determinant, right? This is a smooth map between smooth manifolds. In fact, remember that we use this map but defined here to show that this is an open set and hence a manifold. So this is something that we have seen before, but now we are going to focus only on GL, not on the whole space. And I would like to compute the differential of this. And the differential of this is the trace. Okay? And step by step, we are getting to what we care. This is the tangent space at the identity. Right, so remember that this is going to be this Lie algebra. Is more than just a finite dimensional vector space. But we're getting there. Okay, so let's prove this result. Now, the differential. And the way to compute this, we use the same formula or the same argument as before. We take a curve, some properties, and compute it. The only difference is that we are going to take a very particular curve. And that will help us improving this. So this is the curve that I take. So I have X, an n by n matrix. Right, remember here that this is an n by n matrix. So I take in the exponential of that. And when I take t equals to 0, I get the identity. And remember the other property that the other proposition that I didn't prove, what is the differential of this? So just like in calculus, you take the derivative of the exponent, and the rest is left like this. In particular, if you evaluate the derivative at t equals to 0, you get x. So this curve is the one that we can use to compute this. At 0 equals the identity, and the derivative at 0 is precisely x. Good. So there we are. That's just the definition of the differential. Well, sorry, basically I'm just replacing what x is. And then we use the definition of the differential here, right? Now, I will use the explicit description of the curve. And what is this? Is e to the tx. So I have it like this, right? Now, what do I do next?
We can use one of the properties above that relates the determinant with e to the trace.
Right. We use that proposition, right? So the determinant is e to this, right? Nice. And now what? Again, just notice this. This e is the notation that we use today for a matrix. And this e is the one from calculus, right? Because this is a number, a real number. So this is the e from calculus. Okay, so we take the derivative of this, and I will get something like this. Right? And finally, I have to evaluate at t equals to 0. So again, this is the number. This is not a matrix. This is a number. So I will get e to the 0, which is 1. Not the identity matrix. I get 1. And we are done. So the determinant, the differential of the determinant of the identity equals the trace. Okay? Any questions here? So we have proved this. Okay, and I think this is all that I have so far. Are there any questions?
No, I don't think so.
Moises?
Nope. Everything seems good.
Okay, now. So let me say the following then. I'm going to list the same partial list of matrix groups that we have. GLM is open in Euclidean space, so the tangent space of the identity is the set of n by n matrices whatsoever. Now, what we're going to do is to give us a description of this. The same for this one. And the rest, UN and SUN. Let's stick only with the real ones. So up to here. Now, this is inside of this. Also, this one lies inside of this. Then, this is a subspace of this. This is also a subspace of this. So we are going to describe what type of matrices do we have here and here. We know that this is a subspace of n by n matrices, but which ones? Okay. Now, so let's recall. What is the definition of this? The group SL is the set of non-singular matrices such that
The terminal is 1.
right. Okay. So take any vector. Then we know that any vector, we can write it has a curve, I'm going to put this. This is a curve in the group, such that at 0 is the identity, and the differential of 0 is x. Okay? So far, so good? Now, this is in here. That implies that the determinant of this n by n matrix equals to 1, right? For all t. If I take the derivative of this, on one side I will get 0, because it is a constant, right? The derivative of this with respect to t is 0. Now let's compute the derivative of this with respect to t and evaluate it at 0. So what is this for what you have learned? What is the derivative of the determinant? Salvador, your mic is off. I didn't hear you.
It's the trace.
The trace.
Yeah.
The trace of
At 0.
like this. But the trace, is this correct? I'm missing this, right? The derivative of this. So this is precisely the trace of x. So what do we have? If I have any vector here, right? So for any vector, I get that the trace must be 0. Okay? Now, what can you say about the set of all matrices that have trace 0? What is the algebraic structure of that? you can even tell me how to write such a matrix. How will you write a matrix like that? You can put whatever you want here, except I just decided to take the lower part. Here, you must put the negative of the sum of the other entries on the diagonal, right? So that's how you can write any matrix here. And at the end, you will have and so on. What can you tell me about that set? This
Is a group from
a group under what?
with some.
Exactly. So it's not only a group with the sum, it is a vector space. This is a vector space of dimension what? Right? Because only one entry you cannot put whatsoever. You're missing one entry. Okay? Now, I don't remember if we discussed the dimension of this Lie group. No? Oh, come on. Well, okay, so let's see what we have then. So this is a vector space, and by the proposition is a subspace of this. Okay? Because we saw that, sorry, the other way around. This is a subset of this, right? Because I took any matrix whatsoever and I show that it belongs here. Okay? If we knew the dimension of SL, which happens to be n squared minus 1, we are done. Exactly this space is this one here. So the Lie algebra and with this I will end the class. Usually they use these German letters. It's the set of traceless matrix. That's how they are called. The trace is 0. So this is a vector space of dimension n squared minus 1. And exactly this description is what I meant when I wrote this. We will describe each one of these vector spaces as a subset of matrices with some property. We will have a complete description of those. Okay, so check the notes. If you say that we didn't compute the dimension, then we will work it out. But it is precisely n squared minus 1. And that vector space is this one here. Okay? And so I don't know if tomorrow or maybe next week we will see the same for ON. What type of matrices is the Lie algebra, and continue studying Lie algebras of this type of matrix groups. Great. So with this, we are done for today. I don't know if there are any questions or comments. Okay, so see you tomorrow then.
So yeah.
All right. See you tomorrow.
Bye.